Hello dear friends, I am Vivek Badgujar from the Department of Chemistry, Pratap College, Ammandir. I welcome you all for the lecture series on Hammett linear free energy relationship. In this lecture, we will discuss Hammett plot, first Hammett plot, then we will study the derivation of the Hammett equation, substituent constant, reaction constant, use of Hammett equation and calculation of small k, which is nothing but the rate constant, and the capital K, that is ionization constant. Then we will study the new set of substituent constant, that is sigma plus and sigma minus. Then the most conceptual part of this lecture, that is deviation from the straight line plot. Then we will study the Taft equation, which covers the steric effect, then steric parameter, that is S and delta. So let's start with the first Hammett plot. In 1933, Hammett established the relation between the molecular structure and chemical reactivity. Molecular structure and chemical reactivity. Here he considered the two reaction, that is reaction of methyl ester with reaction of methyl ester with trimethyl amine, and studied their rate constant plus in methyl plus, and he compared the rate of this methyl reaction of methyl ester with their ionization of their corresponding acid, which is denoted by capital K. So Hammett carried out the reaction of series of reaction of methyl ester with this trimethylamine and studied their rate constant denoted by small k, and also he carried out the ionization constant of the corresponding acid of this methyl ester and studied their ionization constant. And after having the value of small k and capital K, he plot a graph of minus log small k of a versus minus log of capital K. And surprisingly, he found that the straight line relationship. He found that the straight line relationship. And this this K, capital K and small k, both are related with the Gibbs free energy. Related with the Gibbs free energy. This this relation is then referred as a linear free energy relationship. I am repeating again. Hammett carried out two reactions. In first reaction, he studied the rate constant, and in second reaction, he studied the ionization constant of the uh, corresponding acid of this methyl ester, and plot a graph of a minus log of small k versus minus log of capital K. And surprisingly, he found a straight line. Surprisingly, he found a straight line relationship between these two reactions. And as both small k and capital K are related with the Gibbs free energy, this relationship is then referred as a linear free energy relationship. Now, after having this surprising result, he carried out another reaction, that is base catalyzed hydrolysis of ethyl ester, base catalyzed ester hydrolysis of ethyl ester. Here R is either meta or para substituted benzoic acid derivative, or ortho substituted benzoic acid derivative or aliphatic acid derivative. And in same way he studied the rate constant of these reactions, and then after carried out the he studied the ionization constant of this of the corresponding acid of this ethyl ester. And but this time the results obtained are not encouraging, as in this case some of the substituent or some of the ethyl esters are appear on a straight line, but ortho esters ortho esters as well as aliphatic esters are appear out of the straight lines, are lie far far apart from the straight line. And after observing that, he concluded that this linear energy relationship, the linear free energy relationship, is not generally applicable for the ortho substituted benzene derivative and aliphatic species and this relationship is only applicable for the meta and para substituted benzoic acid derivative, only applicable for the meta and para substituted benzene derivative. Now, what is the explanation or uh, what is the effect behind this? The if we if we study the base mechanism of the base catalyze of this ester hydrolysis, we find there is a formation of tetrahedral intermediate. There is a formation of tetrahedral intermediate. Now, when this tetrahedral intermediate is formed, in case of meta and para substituted benzoic acid derivative, we can easily see that we can see that this meta or para substituted benzoic meta substituent is far away from this tetrahedral intermediate. But when we study the tetrahedral intermediate for the ortho substituent, we can see there is a huge steric crowding between this ortho substituent and this tetrahedral intermediate. And same type of steric crowding occur in case of aliphatic ester. Here also this R group and this tetrahedral intermediate causing the and this R group is causing the steric crowding in the formation of this tetrahedral intermediate. But if we studied the ionization constant of the ortho of the ortho substituted benzoic acid, in this case there is no such a formation of tetrahedral intermediate, no such a formation of tetrahedral intermediate, and the steric crowding in the reactant as well as in the product is almost the same, and therefore there is no effect of this ortho substituent on ionization constant. So in case of ortho, and in same way in case of aliphatic esters, no such a steric crowding is taking place. No such a steric crowding is there before the before ionization and after ionization. But such a steric crowding is appear in or can be seen in base catalyzed ester hydrolysis. So in case of ortho and aliphatic ester, in case of ortho and aliphatic ester, the one of the reaction that is base catalyzed ester hydrolysis, or the rate constant of this base catalyzed ester hydrolysis is depend upon polar effect as well as steric effect. But at the same time, the ionization constant is not affected by the steric coding, and it is only affected by the polar effect. And therefore, one of the reaction, uh, two factors are responsible uh, for the one reaction, and only one factor is responsible for the another reaction. And therefore, in case of ortho ester and aliphatic ester, we have a random plot. We have a random plot, that is non-linear free energy relationship, as we do not have the straight line relationship. But at the same time, in case of meta and para substituent, both reaction, that is base catalyzed ester hydrolysis as well as ionization constant, both reactions are only affected by the polar effect. Polar effect, that is inductive effect and resonance effect, and no such a steric crowding is present for the ester hydrolysis as well as ionization constant. And therefore, in case of meta, and therefore for meta and para substituent, we have a straight line relationship. And therefore, this is Hammett equation is applicable only for meta and para. This is the reason why the Hammett equation is applicable for meta and para substituent, where zero steric effect or no steric effect is there. Next is a derivation of the Hammett equation. Now first, this Hammett equation, I am repeating again, this Hammett equation is only applicable for the meta and para substituent, as it shows the straight line relationship. And as we have a straight line, we can derive this Hammett equation using the straight line equation, that is y is equal to mx plus c. So same, this straight line relationship is applied for the Hammett straight line plot. Thus, for a substituted species, we have log kx is equal to rho into log kx plus c, where this small kx is a rate constant for the uh, ester hydrolysis, and capital Kx is a ionization constant of the substituted benzoic acid. Rho is a reaction constant and C is a constant. Now rho is a reaction constant, which is the nothing but the slope of a straight line, which is obtained from the slope of the straight line. Now similarly, we have a straight line relationship for the unsubstituted ester species, which can be given as log small kh is equal to rho into log kh plus c. Now by subtracting the equation for the unsubstituted compound from the substituted one, we have this equation, where this c get cancel out, and we have log kx upon kh is equal to rho into log kx upon kh, where log kx upon k is a then refer as a substituent constant, and this log kx upon kh is a rate ratio of a rate constant, and rho is referred as a reaction constant, is referred as a reaction constant. So in the summary, we have in this lecture we have discussed the Hammett first plot. Then after we studied this Hammett relationship is only applicable for the meta and para, where only polar effect is responsible for the rate constant and ionization constant, and no steric effect is there. No steric effect is there. Then after we studied the derivation of the Hammett derivation of the Hammett equation using the straight line relationship. In next lecture, we will discuss about the substituent constant and reaction constant. Thank you.